Here we're given a periodic signal, x of t, and we're asked for the Fourier series expansion. So, to write x of t as a Fourier series, remember it means finding these terms, the a terms and the b terms. So you've got the cosine series and the sine series. So finding the Fourier series means finding these three sets of numbers. So because x of t is clearly odd, we can say a naught is 0 and a n is 0. So these terms are 0. We don't have a cosine series. All we need to find is the bn. So it's much easier now. So to find bn, the expression for bn is 2 over t, the integral from 0 to t, x of t sine n omega naught t dt. So t is some constant that we need to find, and omega naught is also some constant that we need to find. So that's easy. We can find omega naught as a function of t because it's simply 2 pi over t. We also need to find x of t. So x of t is this straight line here. So x of t, we need to find the slope, the gradient of x of t. So we can do that simply by looking at that. That value is a. And if you divide that by that, you can say x of t equals a divided by t over 2 times t, which is simply 2a over t times t. So that would go in there. So now we can write bn, and instead of integrating from 0 to t, we could integrate from minus t over 2 to t over 2. So that will make it an easier integration. So bfn is the integration 2 over t from minus t over 2 to t over 2, 2a over t times t So now we have this integration, and we'd need to integrate by parts. And if you do that, you'll get the following result. Let me put that down here. So bn will give you 4a minus cosine n pi over 2 pi n Okay, now cosine n pi we can simplify because we know that cosine n pi is simply, it's either 1 or minus 1, so it's minus 1 to the power n. and sine n pi is always 0. So now we can rewrite b of n as 4a minus 1 to the power n over 2 pi n plus 0. And you can add that minus to that minus, and you have 2a over pi n minus 1 to the power n plus 1. So that's my b term. Remember, what we're trying to find is the Fourier series. So what we wanted was that. And we've just found the b term. So now I can write my final answer, x of n equals, or x of t, equals summation from n equals 0, or actually n equals 1 to infinity, 2a over pi n. So that is simply that. This is your bn multiplied by, oh, let's put the minus 1 first, multiplied by sine n omega naught t. Now we need to replace omega naught with 2 pi over t, so it'll be 2 pi over t, t. So this is the final answer for part A. This is my Fourier series representation. So anything less than this will be an incomplete answer. This is my Fourier series of x of t. Now for the next part, it asks for the first 6 spectral components. So it's asking for n equals 1, 2, 3, 4, 5, and 6. And what it wants is Cn. Cn we can calculate from An and Bn. Now An we know is 0, so Cn and Bn are going to be the same. So in this case, they're the same. So the A's will simply be 0, 0, 0. Now the B's, we need to substitute in here. So this is the expression for B. So we need to substitute n equals, here, n equals 1, n equals 2, n equals 3, etc. Now the problem is we don't know the value of A. So we can just put it in terms of A. So we'll just stick an A on the end. So if you put these in your calculator, for n equals 1, you get 0.637. For n equals 2, you get negative 0.318. And the values of C will be exactly the same. Now the question is to sketch. So calculating these components is only the first step. The next step is to actually sketch them. So we'll have a horizontal, it's going to be a discrete plot. The horizontal axis will be n. The vertical axis will be the magnitude of c of n. And we'll actually divide by a because we have a's for each of these. So if I have a scale of 0, let me change the color. So if I have 0 0.1, 0 0.2, so the first one is 0.637, so that's right there. The next one is 0.318, that's right there. The next one is 0.212, right there, there, and there. And you can add stalks to these to make it clear it's a discrete signal and frequency. Oops. And you have at n equals 0, you have a 0. So that's 0, 1, 2, 3, 4, 5, 6. So this is what you would need for full mark for part B. The first 6 spectral components. So n equals 1 to 6, but you always include the DC term. The next part says find the average power of x of t. Now x of t is a continuous time signal. It has infinite energy but finite power. So we can find the power by definition. It's 1 over t, the integration over one period, minus t over 2 to t over 2, x squared of t dt. And we've already found x of t. We said x of t is simply, I think it was a over 2t times t. Or no, it was 2a over t. Yeah, it was 2a over t times t. So the integration will be 1 over t, the integration from minus t over 2 to t over 2, 2a over t times t squared dt. So that gives me 1 over t times 4a squared over t squared, t cubed over 3 from minus t over 2 to t over 2. And if you substitute your limits there and you cancel out the t's, you get an answer of a squared over 3. So that's the final answer for the power. So to find the power, we simply integrate over one period. This is the formula for power. And that's your answer, a squared over 3. So we don't know a, so we can't find the power, but we found the power in terms of a. For the next question, it says how many harmonics would be required to retain, that means to keep, at least 90% of the signal's power. So the signal's power is a squared over 3. So we want 90% of a squared over 3. So we want to retain 90% of a squared over 3. So that's 0.3 a squared. So that's our target. We want at least 0.3 a squared. So what we need to know is how much energy we have in each of these harmonics. So what we can do is simply calculate that individually. So each harmonic is a sine wave with an amplitude of Bn. So let's look at each of these harmonics. 1, 2, 3, 4, 5, 6. So what we want is Pn, which is the power of the nth harmonic. So let's just remind ourselves, x of t is a summation from n equals 1 to infinity of Bn times sine n omega naught t. What's the power of each of these harmonics? Now remember, it's a sine wave, so the power of each harmonic is simply b squared over 2. So all we need to do is take the component b, which we found up here, so each of these squared divided by 2. So here we'd have b1 squared over 2, b2 squared over 2, b3 squared over 2, etc. So each of these will have an a in it, so I can simply divide by a squared. So the first one is 0.203, 0.0506, 0.0225, 0.0126, 0.00806, so just as a reminder, each of these is simply b squared over 2. So that's b1 squared divided by 2. And that's b5 squared divided by 2, etc. So, but that's not the question. The question is how many harmonics? The question is how many harmonics? So the answer would be something like 4, 5, 3. The question is how many harmonics do we need to retain 90%? So we want 0.3 a squared. So how many of these do we need to add together to retain 0.3? So if I put a cumulative power here, so k equals 1 to n, p of n, and I divide by a squared. So the first harmonic is simply 0.2. If you add the second harmonic, so you add these two together, you get 0.2535, and you add the first three together, you get 0.276. If you add the first four together, you get 0.2886. If you add the fifth harmonic, you get 0.2966. And if you add the sixth harmonic, you get 0.3023. And the question was at least 90%. So we want at least 0.3 a squared. Here you have 0.3023 a squared. So how many harmonics do we need? We need at least 6, because this is almost, or actually what I should say is this is greater than 0.3 a squared. Therefore 6 harmonics are needed. And that's your final answer. So the answer is 6 harmonics. Okay? To arrive at that answer, we would need to do all this work. 6 harmonics are needed. The next question says, this same signal, so the signal, when it says the signal, it's talking about x of t, the sawtooth waveform. It's passed through a low-pass filter. What does a low-pass filter do? A low-pass filter allows low frequencies to pass and blocks the high frequencies. So remember, our spectrum looks something like this. That's our spectrum. And it's passing the signal through a low-pass filter, so it's going to allow some components to pass and some not to pass. The question is, if you know the cutoff frequency of the filter, what's the Fourier series of the resulting signal? So we also know that there's a clamping circuit where 1 volt of DC is added. So x of t will now have an A naught of 1. So our new signal is no longer x of t, it's y of t. So we're now trying to express y of t. And y of t will be the same as x of t, except it'll have fewer components. So it'll have a DC term, and instead of having n equals 1 to infinity times bn sine n omega naught t, this will be replaced by some value. And we need to find that out by looking at the cutoff frequency for our low-pass filter. So let's work on that step by step. Let's move this out of the way. And let's figure out from what we're given. We're given t equals 1 millisecond. So that means that f naught is 1 over t is 1 kilohertz. So how many components will be allowed to pass if the low-pass filter has a cutoff frequency of 4.5 kilohertz? It means the fundamental will pass, the second harmonic will pass. The third harmonic will pass. So the first the fundamental will be 1 kilohertz. 2 kilohertz, that'll pass. 3 kilohertz, that'll pass. The fourth harmonic, 4 kilohertz, that'll pass. But the fifth harmonic, 5 kilohertz, that won't pass. So it'll only allow the first 4 components to pass. The fifth onwards will be blocked by the low pass filter. So we replace this with 4. So we'll only have components from 1 to 4. So we can replace that with 4. We can replace A0 with 1. We can replace omega naught here with omega naught equals 2 pi f naught. So that's simply 2000 pi. We simply replace that. So we can say 2000 n pi t. And we can replace B of n with the expression that we found back in part A. So if we scroll all the way back to part A, we found B of n right here. That's our B. And we can put that here. So if I erase B of n, we can put that right in there. Okay, we're given A is equal to pi, so I can replace A with pi. That pi cancels with that pi, so I have 2 over n. And that's my final expression. So the question was, find the Fourier series expansion of the resulting signal. So this is my resulting signal. It has a DC term of 1 volt. It has it has 4 components: fundamental, second harmonic, third harmonic, and fourth harmonic. All the higher harmonics are blocked. Now, if you wanted to, you could actually write this out as a series, because you already have the coefficients.